Hello everybody. This video is going to discuss the density of a network. Let's get started by looking at some examples. Pause the video and take a look at these two networks and try to describe how they're different. You probably realize that both of these networks have the same number of nodes. In other words, the order of these networks is the same. In this case, our order is equal to 5. The main difference between these two networks is that they have different sizes. Remember, the size of our network simply counts up the number of edges. In network 1, we're going to have 10 edges, whereas in network 2, we have 4. Focusing in on network 1, remember this is what we call a complete network. Every possible edge that could appear between two nodes actually appears inside of the graph. Network 2, however, is not complete. In this case, there are some edges which are not realized. There are some edges which are missing that would have appeared in the complete version of a network with the same number of nodes. Specifically, all of these edges in the gray dotted lines are missing edges that would have appeared in the complete version of a network with the same number of nodes. Let's consider a third network, a network without any edges. We usually refer to these as totally disconnected. There are absolutely no edges in this network. So to motivate the metric that we call density for a network, we want to think about considering the spectrum. So on the spectrum from one extreme to another, from having absolutely no edges to having every possible edge that could occur with that number of nodes, where does our particular network fall? One way to approach this question would be to label our spectrum with the number of edges at either extreme, and then count the number of edges in our given network and place it along the line appropriately. On our extreme to the left, there are absolutely 0 edges. On our extreme to the right, if we keep our number of nodes fixed at 5, there are going to be 10 edges. In our particular network of interest, we have 4 edges. So if we were to place this on our line, we might put it somewhere here, just off of center. There is a shortcoming to this approach. The spectrum as we have it set up now can really only fairly be applied to networks that have exactly 5 nodes. The minimum number of edges being 0 and the maximum number of edges being 10 really only applies to networks with 5 nodes. If instead we were trying to consider a network with 6 nodes, it could have a maximum of 15 edges if we consider a complete network with 6 nodes. So if we consider networks with 6 nodes, there would be some networks that wouldn't fall on the spectrum if we go only from 0 to 10. So we need an approach that will fix this ambiguity, because oftentimes we'll want to be able to compare networks that have different nodes, different number of nodes. Here's a great way to address our problem. We know that if we have a 5-node network, the maximum number of edges is going to be 10. And if we consider other networks, we'll also be able to compute the maximum number of edges in those cases. So what we'll do is take that maximum number of edges, which in this case is 10, and now let's take all of our edge counts and divide by that value. We're no longer looking at a spectrum of edge counts. We have something different here. However, when doing this, we'll standardize the values that should appear on our spectrum. The totally disconnected graph or network is always going to have a measure of 0. The complete network is always going to have a measure of 1, and then the networks that we want to consider are going to fall somewhere in between. So what we do is we standardize our spectrum to always fall between 0 and 1. We call this new measure, or new metric, the density for a network. Here's the general idea. The question we're trying to answer is, on the spectrum from totally disconnected to complete, where does our particular network fall? Right? So that we can compare networks with different numbers of nodes, we define this metric called density, where we count up the actual number of edges in our network, and then we divide by the maximum number of edges that would appear in a complete network with the same number of nodes. The nice part about this metric is it will always fall in between 0 and 1. So this way we can compare sort of our edge density between networks with different number of nodes or different orders. Now for a little bit of notation. The number of edges in a given network, which we often refer to as the size of the network, we can represent in the following way: absolute value of E. This is just shorthand notation so that we don't have to write out our text every time. The number of edges in a complete network with a fixed number of nodes. So in this case, let's let little n represent the number of nodes in the network that we're considering. There's a very nice formula for this, and I'm going to hopefully record another video that shows you where this number comes from. But in a complete network with n nodes, the total number of edges present can always be computed as n times n minus 1 divided by 2. Some really neat mathematics goes into this. So, here's our new formula for density. If we take the number of edges in our network, we'll see this absolute value of E appearing in the top, and then we're going to divide by this n times n minus 1 over 2. Since we're doing a double division, the 2 ends up swinging up into the top. If you don't remember that, that's fine. Okay, so let's look at a quick example. Suppose we have our network, and we want to compute the density for this network. The first thing we would do is count up the number of nodes and the number of edges. So in this case, the number of nodes is 6, 1, 2, 3 across the top and 3 across the bottom. Our number of edges in this particular network is 7, 1, 2, 3, 4, 5, 6, and then 7. And now we can just plug these numbers into our density formula and simplify in order to get the density. Now once again, density is normalized to always fall between 0 and 1. So we could compare the density that we get with this network to the one that we had in our previous slide. In this case, we'll get 14 over 30, which is approximately 0.467. Our previous network had a density of 0.4, so this network would be considered more dense. A couple of things to keep in mind when you're looking at the density metric. If your density equals 1, you know that you have a complete network. If your density equals 0, there are no edges at all. This is called a totally disconnected network. You can interpret density as being the proportion of possible edges realized in the network. In our previous example, we saw that the density of network 1 here is 0.467. That means roughly 46.7% of all the possible edges actually occur in the network. The last thing to keep in mind is typically as the number of nodes in your network increases, the density measures tend to decrease. So if you're comparing two networks that have vastly different number of nodes, the density measure may not be perfect. Remember our bucket brigade network? In this case, we have n nodes connecting in the following way. Can you find a formula for the density of this network that depends on the number of nodes in the bucket brigade? Your answer should include n. Good luck!